Okay, let's dive into this. Today, we're taking on a challenge that feels honestly more urgent than ever before. We are going to build a foolproof BS detector for navigating today's totally wild information landscape. We're exploring the entire spectrum of scientific truth so we can definitively separate fact from fiction. I mean, just think about the claims we're bombarded with on a daily basis. Is 5G a mind control experiment? Is the Earth flat? And has NASA just been covering it up this whole time? Was COVID-19 engineered by the vaccine industry to make a quick profit? You've absolutely seen these kinds of sensational ideas floating around online. And these provocative questions establish a really urgent need for us. We literally have to be able to differentiate rigorous, actual science from contrived conspiracy theories. But, how exactly do we do that? So here is our roadmap for this explainer. 1. Defining science and pseudoscience. 2. Building good scientific models. 3. The power of peer review. 4. Navigating the gray areas. And 5. The ultimate litmus test.
Let's start right in with part 1, defining science and pseudoscience.
The absolute trickiest part about this whole landscape is that both science and pseudoscience are heavily presented to the public as sound science. They both publish information, and they both use highly technical, really scientific-sounding concepts and terminology. In fact, pseudoscience actually goes out of its way to dress up in that language to sound credible. But the core drivers, they couldn't be more different. Science is fundamentally driven by evidence that can be tested, replicated, and subjected to rigorous peer review. Pseudoscience, on the other hand, is driven primarily by commercial, monetary, or cultural goals. So while they might look identical on the surface, their core engines, and especially their willingness to be tested by others, are entirely opposite. Moving right along to part 2, building good scientific models. You see, the primary task of science is to explain observations in the real world, and scientists do this using models. A scientific model is essentially a simplified description of reality that captures patterns to agree with measurements. Think of astronomy, which is one of the best historical examples. Astronomy has always been about finding patterns in the motions of celestial objects. Visually speaking, once you know the patterns, a scientific model gives you a curve that quite literally connects the dots between data points. And crucially, this model has to be simpler than just dumping all your raw data into a massive pile. And this brilliantly illustrates the difference between a true explanation and a mere statement. Take Darwinian evolution. It is a fantastic scientific model because it actively connects the dots of how certain organisms evolved from each other, using a few simple rules to explain a massive amount of biological data. On the flip side, look at creationism. Creationism simply posits that the Earth was created with everything already exactly in place as it is right now. This means it puts in exactly as much information as you get out of it. It doesn't connect existing dots, it just says, well, it is what it is. Because it completely lacks that explanatory simplification, it is inherently unscientific. But what happens when someone just forcefully draws wild, erratic lines to connect the dots in a way that fits their preconceived beliefs? Well, that introduces a massive mathematical pitfall known as overfitting. Overfitting happens when a model has so much freedom and so many free parameters that it can be twisted to fit literally any data. When you do this, the model actually stops explaining anything at all. You just end up having to invent incredibly contrived assumptions to explain a very tiny amount of observations. Let's look at how this exact concept of overfitting acts as the driving engine for conspiracy theories. If you claim the Earth is flat, your model immediately clashes with a mountain of existing data. To make it fit, you have to invent massive, totally contrived assumptions. I mean, you have to assume it's somehow possible to flawlessly fake all NASA data and images for decades. You have to assume someone has managed to brainwash every single airline pilot in the world, which logistically sounds like an absolute nightmare. These absurd assumptions are mathematical overfitting in action. It makes the theory completely unscientific compared to the beautifully simple, factual explanation that requires almost no assumptions. The Earth is round. Which brings us to part 3, the power of peer review. When claims actually get tested, you immediately see this massive behavioral split. A true scientist operates with an open mind. They follow unbiased data wherever it leads, even if it totally destroys their own pet theory. A pseudoscientist, they have a closed mind. They start with a preconceived conclusion and cherry-pick the data to protect it, aggressively rejecting anything that contradicts them. Science thrives on facts and constantly revises itself as new info comes to light. Scientists genuinely get excited by harsh critique. Pseudoscience, though, relies on a stagnant faith of just believe me and forcefully rejects any skepticism.
Let's dive into part 4, navigating the gray areas.
As much as we'd love everything to be perfectly black and white, we have to deal with the messy middle. The first gray area is tentative science. This is that cutting-edge science at the very starting point of the peer review process. It hasn't been widely tested yet. A great example of this is string theory in physics. It's constantly advertised as highly promising, but string theorists haven't yet produced a model that actually fits the data and is practically useful. It's an idea in development, just waiting for rigorous testing to see if it makes the cut to become accepted science.
The second gray area is bad science. This is your poorly designed experiments or studies where the data is interpreted using faulty logic. Now, what's really interesting about this slide is that bad science can actually still remain under the umbrella of legitimate science. How? Well, if the researchers advocate for rigorous testing, submit their flawed work to peers, and then humbly accept the scientific community's rejection of their claim, they are still participating in the scientific process. They followed the rules, even if their experiment was a bit of a mess.
So how do tentative science and bad science eventually devolve into pseudoscience? It happens through a very specific two-step behavioral process. Step 1, the creator stubbornly suppresses rigorous testing and actively rejects those negative peer reviews from the scientific community. Step 2, they take that rejected or untested claim and falsely present it to the public as accepted, sound science. The exact moment you reject the community's feedback and pretend you have the final, unquestionable truth, you cross the line into pseudoscience. Part of navigating this gray area is knowing what not to be impressed by. A lot of pseudoscientists absolutely love to brag about making lucky predictions, but a prediction alone means nothing. I could randomly guess that a relative of yours will fall ill this week. Just by sheer coincidence, for some of you watching, I will be right. Are you impressed by my scientific genius? No way, because a random guess without a transparent model or stated assumptions explains absolutely nothing. To be a scientific projection, I'd have to show a model that is statistically far better than a simple random guess. Let's move to and see how this builds our understanding of models that don't think exact predictions, but are still incredibly rigorous science. Pandemic and climate models are perfect examples of this. It is basically impossible to predict the exact future spread of a virus because real-world spread depends on completely unpredictable human policy decisions, like whether we decide on a whim to cancel large events or not. Instead, these models provide scenarios or if-then projections. If we cancel events, it looks like this. If we don't, it looks like that. They are highly scientific because they accurately describe vast amounts of existing data, like the historical spread of epidemics or human-caused CO2 increases, using incredibly simple explanations with very few assumptions.
So, the crucial point is, we've arrived at part 5, the ultimate litmus test.
We've defined the engines of science and the pitfalls of overfitting. So here is a practical tool you can use every single day. I want you to imagine posing one simple question to anyone making a bold, sensational claim online. Whether they're pushing a new miracle diet, claiming 5G is dangerous, or presenting a radical new theory of physics, ask them directly, what would change your mind? Their answer will instantly reveal their credibility. If you ask a true scientist this question, their answer will be immediate and simple: evidence. A true scientist is fundamentally driven by data. They are open-minded, and they are always willing to revise their knowledge based on rigorous, peer-reviewed proof. If the data goes against them, they just follow the data. But if you ask a pseudoscientist what would change their mind, their answer is starkly opposite: nothing. No amount of data can break through a closed-minded belief. When you rely on faith over facts, you completely insulate yourself from the truth. So the next time a viral claim pops up on your feed, ask yourself, is the person selling this willing to be proven wrong? Because if they aren't, why should you give them your time?